Right. So in your last class in photochemistry, we discussed what is Barton reaction and some selective functional groups, especially in Barton reaction. So there is a transfer of hydrogen takes place from delta carbon to corresponding alkoxy radical. Then nitration will take place on delta carbon. And final answer is gamma hydroxy That is called Barton reaction. Okay. Suppose see, if there is a presence of only complete name. Okay. So small announcement for online students. So those who are login in online, try to log in with your name. Okay. So if you are login with your different names and if you log in with a different candidates, that won't be accepted. Okay. So try to log in with your original name itself, especially for online students only. Right. So take some applications on Barton reaction. See what is the requirement of this one? This is ONO. Photochemically is given. There is a requirement of delta carbon. Delta carbon minimum alpha, beta, gamma, delta. Delta required minimum 2 hydrogens. So on that time, this you write down OH, this you put N double bond OH, oxygen. So there is a fourth carbon is required. See, this is photochemical irradiation, alpha, beta, gamma, delta. Fourth carbon are not, 2 hydrogens are there. When molecule having 2 hydrogens, put double bond N and this is OH. Fourth carbon should carry minimum 2 hydrogens. See, this is fourth carbon, but fourth carbon having only alpha, beta, gamma, delta, having only 1 hydrogen. When 1 hydrogen is present, oxime formation won't take place. You will get only nitration. Only NO formation takes place. This never give oxime, because here there is no presence of one more additional hydrogen. If minimum 2 hydrogens are present, 1 hydrogen transfers from here to here, then you will get OH. Other hydrogen responsible for tautomerism. Suppose if only 1 hydrogen is present, so on that time transfer that hydrogen to oxygen and this radical combine with NO and forms nitration product. Only one product is possible. Suppose see, this is fourth carbon. This is ONO. Photochemical if you take alpha, beta, gamma, delta. Even though delta adjacent highly reactive carbon is present, still your answer remains same. So there is no rearrangement will take place. Here this is OH and here double bond OH. That is the answer. Right. Always fourth carbon just replace with hydrogen with NO. That NO undergo tautomerism will give oxime. ONO. So try to count numbering from nitrite 1. See 1, 2, 3, 4 delta. Here alpha, beta, gamma, delta. Alpha, beta, gamma, delta. Delta having no hydrogen, no reaction in this one. If there is no hydrogen, no reaction. No Barton reaction. Barton reaction not possible if delta carbon having no hydrogen. Now this is 1, 2, 3, 4. Use this hydrogen. This is ONO. So photochemical, what is the answer? This is alkyl. R is nothing but alkyl. Anyone you can take. Methyl, ethyl, you can take anyone. Especially it is used in steroids. Barton reaction is most important reaction in steroid. Here what you write? Can you target this one? Write double bond NOH and write down OH. Here also double bond NOH, no reaction, and here double bond NOH. Target this one. 1, 2, 3, 4. Put double bond NOH, oxime. Every time oxime is the answer. So this is a question, simple question given in CSR. This is given, straight chain. 2 years before it is given, 2022 CSR examination it is given. Nitrate only one top reaction is there, alpha, beta, gamma, delta. Fourth carbon, just remove 2 hydrogens, put double bond NH. Here double bond NOH. That is the answer. ONO. This is methyl and here ONO. Here hydrogen, C double bond. What is the answer? Which is fourth carbon here? Alpha, beta, gamma, delta. 1 point I given yesterday. Always gamma carbon hydrogen is cis2 nitrate. If fourth carbon, if it is not cis2 nitrate, that carbon hydrogen never transfer to oxygen. Okay, always fourth carbon. 1, 2, 3, 4. This carbon hydrogen should be cis2 nitrate. Then only transfer this hydrogen from here and this nitration will take here. So, what is your answer? Can I write thick line here? Write hydroxy and write dotted line. This is thick line. Here you will get nitrogen and here you will get nitrogen double bond like this. See, here carbon is there or not? This carbon connected to nitrogen. So this is nitrogen and this is OH, oxime. Okay, and this part will be as usual. This part will be unaffected, 5-membered, thick line, and this is dotted line. Clear? Fourth carbon hydrogen transfers here. this NO add here. So when you add this NO, initially you will get N double bond O. Here how many hydrogens are there? 2. So one of the hydrogen involved in tautomerism, you will get this one. Oxime. Fourth carbon is your target site. Fourth carbon, that two cis to each other. And here see, this carbon, just you remove 2 hydrogens, put double bond N OH. And see in this one, this is alpha, beta, gamma, delta. This hydrogen is cis 2 ONO. So if it is cis 2 ONO, this is thick line. Here see, this is R. That R is methyl group. And here there is a presence of OH. Here is it thick line or not? Thick line. Carbon, nitrogen double bond. And here I can write OH. Okay, so these functional groups are unaffected. C double bond O. This dotted line as it is. And here also dotted line as it is. They are unaffected. Every time first what happens? See, when NO added here, first N and double bond O formation takes place. Then this hydrogen involved in tautomerism. After tautomerism, put double bond here, put OH here. That is the answer. Okay, always delta carbon. Your target is delta. Alpha, beta, gamma, delta. Delta carbon and nitrogen should carry double bond. And delta carbon, minimum how many hydrogens are required? Minimum 2 hydrogens. ONO, a dotted line, and this is dotted line. This is C double bond OAC. Photochemically, what is the answer? So these are CSR questions. So what is the requirement? Delta carbon or not? Fourth carbon. Alpha, beta, gamma, is it delta? Now right side even, this is beta, alpha, beta, gamma, delta. Both deltas are present or not? When both deltas are very closer, on that time, this is highly preferred because it is very closer to this oxygen. Arrangement is very closer to this because it is chair form, it is also chair form. So out of these two chair forms, this chair form angular methyl is very close to this one. So when these two are competitors together, give priority for this methyl. Clear? So can you give the answer? This carbonyl group is unaffected. This is dotted line. Can I write thick line here? Carbon, nitrogen double bond, and this is OH. And here, is it thick line or not? Thick line. This is double bond OAC, and this is methyl, angular methyl, and this is dotted line. That is the answer. Right? Be careful with these 2 points. See, this is normal numbering. 7, 8, 9, and this is 10. 11, 12, 13, 14, 15, 16, 17. This is 19. Methyl is 19. This is 19 and this is 20. Already in stereochemistry this numbering is given. This is 19. This is 19 angular methyl and this is 18 angular methyl. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then 11, 12, 13, 14, 15, 16, 17, 18, and this is 19. So this one is 18. So this is also CSR question. For 4 marks it is given. What is the answer? So now this is predominant or not, alpha, beta, gamma, delta. First what happens? Delta hydrogen migrates from here to here. Then this becomes alcohol or not? Similar. Here also this nitrate becomes alcohol. So then here what you will get, radical or not? This hydrogen once if they transfer here you will get radical. So after getting radical, here double bond O. This is double bond OAC. This is methyl and here it is angular methyl. And here one radical. This is thick line and there is a formation of OH. Can I? What is removed here? NO. See in this one. First I would like to break nitrogen oxygen bond. And here 3 hydrogens are there. Here 3 hydrogens are present, in which one of the hydrogen I transfer from here to here. Then this NO starts coming from here to here or not, for second molecule. So whenever if NO is coming from here to here, adjacent one double bond is present. This double bond undergo homolytic fission. Then what happens? See, this radical join together. And here this radical is left. This radical is conjugate to carbonyl. This radical is taken by NO. So now nitrization will take on this carbon, not on this carbon. So now This double bond undergo homolytic fission, radical forms a ring. So once if ring formation takes place, this is thick line, dotted line, C double bond O. Is it alcohol or not? This is OH. Then see, this radical join together, this and this. Can I write a 3-membered ring? And what is left here? Radical. This radical combined with which one? NO, N double bond O. Right? Actually where that NO should be added? NO added on this carbon. But this carbon having a adjacent double bond. That's why this radical is this radical is allyl radical. That radical is get disturbed by this double bond. So this radical combined together and forms a 3-membered ring. Then this radical combined with this NO forms nitrosation. Now this is involved in tautomerism with hydrogen. Then put double bond here and see there is a formation of oxide. That is your final answer. If any double bond is conjugate to allyl carbon, the double bond responsible to give 3-membered and corresponding terminal double bonded carbon will take that NO radical. Then NO radical becomes oxide. This is called oxide. Right. See, this is one 5-membered ring and I am writing chair. So here I am writing N double bond O. Photochemically, what is the answer? See, this is alpha, beta, gamma, and here it is delta. Delta carry 2 hydrogens or not? It is very close to nitrite. So this 5-membered is as it is, Here 6 membered I am writing as it is 1, 2, 3. So this I am writing in the form of OH, and here I am writing N double bond O and here H. Nitrization or not initially? Nitrization. That nitrization responsible to give? What is final answer? Oxime. This is OH and here nitrogen, and always you should write like this. So this hydroxy group develops a chelation. So with this lone pair it will form a hydrogen bonding. You will get oxime like this. Right? Alpha, initially alpha, beta, gamma, delta. Delta carbon carry oxime. Now from here see, if they give any H2SO4. H2SO4 means it is Beckmann rearrangement. Okay, oximes involved in Beckmann rearrangement. Beckmann rearrangement. So what is Beckmann rearrangement? Oxime to amide C. Suppose see this is CS3, here carbon nitrogen double bond and here OH is there, here pH is present. Now this hydroxy and this opposite group, so both undergo rearrangement. I am using H2SO4 oxime. Now this methyl comes from here to here. So after coming this, nitrogen carry methyl. First you write down single bond. And this carbon carry cation. So add water molecule, convert them into carbonyl. Then this nitrogen carry hydrogen. So this is called amide. And what is this? Oxime. Conversion of oxime to amide is called Beckmann rearrangement. Oxime to amide. Now here, this hydroxy, this bond is exactly opposite. Hydroxy and opposite bond. Now break this bond and attack on nitrogen. Okay, so after attack, see here. This carbon connected to this and this carbon connected to nitrogen. So initially there is 6 member is present here. Okay, and here it would be hydroxy. This carbon right now attaches to nitrogen and this becomes a carbonyl. That is the answer. Amide you will get. See, whichever is migrating on nitrogen, that is exactly breaks from here. This hydroxy and migrating group both are opposite to each other. Suppose if I write this hydroxy left side, on that time phenyl is a migrating group. You need to migrate phenyl from carbon to nitrogen. Now which group I am migrating? Which group I am migrating? Methyl I am migrating. Methyl I am migrating from carbon to nitrogen. Break this methyl and migrate on nitrogen. So I migrated on nitrogen. Then methyl attaches to nitrogen. Then this carbon carry positive charge. That carbon reacts with water molecule and forms carbonyl. So they won't mention water separately. H plus separately water is given, that is called Beckmann only. Okay? Simply break bond exactly opposite to hydroxy. This is a bond opposite to hydroxy. This attaches to nitrogen. And this carbon becomes carbonyl. So this carbon is this carbonyl and this is attaches to nitrogen. Conversion of oxime to amide is called Beckmann rearrangement. So this interconversion is very, very important. Photochemically, Barton reaction. This is called Barton. Barton to Beckmann. Very, very important. It is hydrogen bonding. Alcohol, after formation of alcohol, always lone pair will be inside so that there is a formation of chelation. Nitrogen lone pair and hydrogen forms hydrogen bonding. So this is a dotted line, here methyl, here I am writing hydroxy. Suppose if I reacts with NOCl, what is your answer? So what is your answer A? This is on photochemical, what is your answer B? What is AB? Nitrosyl chloride on reacting with alcohol gives nitrite. This I given yesterday. Alcohol reacts with nitrosyl chloride, remove chlorine. This chlorine will take this hydrogen and forms nitrite. This is one preparation of nitrite. This is O, double bond O. This is methyl and this is dotted line. Right? Then what is this? Alpha, beta, gamma, it is delta. It is also delta, but this delta is opposite to this stereochemistry. Always delta carbon and nitrate will be cis to each other. So now this delta hydrogen will be transferred here. Then write the answer. So what is your answer B? So this is as it is, this is thick line, and here I am writing alcohol. This is thick line methyl. Here dotted line attaches to double bond, and here it is NOH, oxygen. This is the carbon. This carbon attaches to nitrogen. Same reaction, NOCl, you will get A. This is on photolysis, you will get B. What is AB? NOCl, nitrosyl chloride. So this is also given in CSR. This is alpha after nitrization, alpha, beta, gamma, delta. Use this carbon. Every time fourth carbon hydrogen is required. So this is cis to each other below. It is below alpha, beta, but this is above. So this can't be used. So see, this is gamma, alpha, beta, gamma, and this is delta. Is it below or not? This is below, it is also below. This is delta, it is also delta. This is gamma delta, it is also delta. Delta, 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 delta. 4 deltas are there. But this is really available delta. Remaining all are not available. So I can write direct answer. Write down 6-membered ring. This become alcohol, thick line. This is thick line. This is dotted line. And here there is nitrogen, this double bond. NOCl A, photochemical B, then H2SO4, that is C. So it is also given in CSR. Interconversion, nitrosyl chloride to nitrite, nitrite to oxime, oxime to Beckmann. Barton, Beckmann, nitration. 3 are most important reactions. This is as it is, and here it is nitration, then followed by B. What is B? Here this is alcohol, this is alcohol, and this is oxime. Always oxime should be written like this. It should be written such a way that it is forms a chelation with this lone pair. Always hydroxy below. Then Beckmann rearrangement, C. So this bond migrate here. So this will be eliminating out, and this carbon becomes carbonyl. So what about answer C? Beckmann product. Now this carbon attaches to nitrogen. Now it is further attaches to carbonyl. It is connected to alcohol. That is the answer. Beckmann rearrangement. First they will ask nitration, then Barton reaction. If any acid medium is given, Beckmann rearrangement. Beckmann is nothing but oxime to, what is this? Oxime. Oxime to amide. Cyclic amide is also called lactam. Cyclic amide, lactams. Cyclic ether is lactone. Ester, cyclic ester, bear vinegar. So that is about Barton photon photochemical reaction. Every time alpha, beta, gamma, delta, delta carbon hydrogens are required. This carbon having 2 hydrogens, 1 hydrogen transfer from here to oxygen, then involve in tautomerism. That will give oxygen. So this is last topic, photo-oxidation or photo-oxygenation. Photo-oxidation. Barton is over. It is the last topic in photochemistry. Photo-oxidation or photo-oxygenation. See, oxidation of organic group. Oxidation of organic functional group with oxygen in light. With oxygen in light is photooxidation. This is also called photooxygenation. We can say photooxygenation or photooxidation, both are same. We are oxidizing a organic functional group or organic group by using oxygen in light. Oxygen in presence of light is called photooxidation or photooxygenation. Suppose if you take at ground state, oxygen is at triplet state. It is not at singlet state. Initially oxygen at triplet state. At ground state, oxygen molecule is at triplet state. It is reverse to multiplicity of organic functional groups. So if you compare organic functional groups, that organic functional groups as well as normal oxygen multiplicity, both are reverse. All organic functional groups having a singlet multiplicity, but molecular oxygen having what is the multiplicity? Triplet state. Molecular oxygen multiplicity is triplet. It is not singlet. At ground state, oxygen is at triplet state, not at singlet state. Okay? Any molecular oxygen at ground state having a triplet multiplicity. It is quite opposite to multiplicity of organic functional groups. If two reagent and substrate both having same multiplicity, then only oxidation possible. Organic functional groups are singlet, but molecular oxygen is what? Triplet. So, normal oxygen is not suitable for oxidation under photochemically. Photochemically, this oxygen is not suitable. This oxygen is not suitable photochemically for making oxidation because it is having which state? Triplet state. So, initially molecular oxygen having triplet multiplicity. Triplet multiplicity is not suitable for oxidizing organic functional groups. But all organic functional groups having what is the multiplicity? Singlet. Initially oxygen is triplet, but triplet is not possible to use for oxidation. Clear? At ground state, oxygen is a triplet state, reverse to multiplicity of organic functional group. Here 1, 2, 3, 4. Here 1, 2, 3, 4. So, single oxygen atom I am taking. What is oxygen atomic number? Oxygen atomic number is 8. So, what is electronic configuration? 1s2, 2s2, 2p4. Below 2 I am not writing, I am writing only 2p4. One oxygen atom, other oxygen atom. Two oxygen atoms I am taking. 2p4, 2p4. So, here how many electrons? 4, 4. Total 8 electrons. So, first you should fill like this. 2, 3, 4, 5, 6, 7 and what is this? 8. What about this one? Sigma and this is pi. What is this? Pi star and what is this? Sigma star. See, is these 2 electrons having same spin or not? When 2 electrons having same spin, what is it? After filling 2 electrons of 2 oxygen atoms in their pi star, now 2 electrons having same spin. Now what is this? What is this state? Triplet state. When 2 electrons having same spin, triplet state. Last 2 electrons. These 2 are last 2 electrons. Last 2 electrons in oxygen, we are filling in pi star antibonding orbital with same spin. Clockwise, clockwise. So that's why this is a molecular oxygen. This molecular oxygen having what is the multiplicity? If 2 electrons having same spin, what is the multiplicity? Triplet. So now this is a triplet oxygen. Normally oxygen having triplet multiplicity, not singlet. Clear? Right. So we can write like this. At ground state, 2 electrons with similar spin. 2 electrons with similar spin present in different pi star antibonding orbital. So now that is known as triplet state. That is known as triplet state. So here it is a ground state triplet where you can write T0. This is a ground state electronic configuration of oxygen molecule. When you fill, see, you know MOT, molecular orbital theory, in chemical bonding it will come. There you identify the spin. Normally 2 electrons should not carry same spin in their ground state electronic configuration. If they carry same spin, they are found to be unstable. But I am saying it is stable because they are occupied in 2 different orbitals. Clockwise, clockwise. When both are clockwise, clockwise, what is the multiplicity? Triplet. So that's why T0, not T1. Because it is ground state or not? Ground state it become T0. Ground state singlet means S0. Excited singlet means S1, S2, S3 like that. Clear? Is it stable or unstable? Stable. Now it is stable. Triplet state of oxygen is stable. That's why it is not a real participator for oxidation. Who is real participator? Singlet. So if I take any triplet state oxygen is highly inert in oxidation. Highly inert in oxidation. Who is a real participator? The real participator is singlet oxygen. Singlet oxygen actually it will do oxidation, but singlet oxygen not exist. See what is real oxidation, real multiplicity of oxygen? Triplet only. If you fill electrons you will get like this only. It is a triplet. But triplet oxygen never do oxidation for any organic functional group. Any organic functional group never oxidized by triplet oxygen. Now I want to convert this triplet to singlet. Then it will be used for oxidation. Initially, without using any light, this oxygen shows a triplet multiplicity. When any molecular oxygen having triplet multiplicity, it is not used for oxidation for any organic molecule. It can't be used because organic molecules are singlet, but they have triplet. So now what is my target? Real participator is what? Singlet only. Triplet oxygen is highly inert in oxidation. They never do oxidation for organic compounds. Who is the real participator for oxidizing any organic molecule? Singlet oxygen. Okay, singlet we need to create. Okay, so especially see, they liberate two types of singlets. They liberate two types of singlet oxygens. First kind. Two electrons with opposite spin. Two electrons with opposite spin in one pi star antibonding orbital. Antibonding molecular orbital. So that is this type. Is it singlet or triplet? Singlet. See, here two electrons present in two different pi star antibonding orbital with same spin or opposite spin? Same spin. Now what I am writing is two electrons with opposite spin in one pi star antibonding orbital. Now what about this one? This is pi star and here also it is pi star, two pi star. Pi star, pi star. It is one singlet. It is a created singlet, not normal singlet. Normally singlets are not possible. So what is the multiplicity of normal oxygen? Triplet only. Remember, what is the stable multiplicity of oxygen? Triplet. So in your MOT this point will be not discussed. Only filling of electron, bonding electron, antibonding electron, bond order, bond length, only this you will discuss in chemical bonding. There they won't explain about triplet states. Singlet, triplet like that. Okay. So if you go through N2, that is different. Go to N2 plus, N2 minus, they are completely different. But only 18, 14 electrons, 16, more than 14. If you compare oxygen molecule, two electrons are same spin. This molecular oxygen is said to be triplet. So they will also write like this. This is called triplet oxygen. Singlet oxygen means they will write number 1 here. Suppose if they not written anything, means it is a triplet only. Because normally if you fill electrons in oxygen molecule, that will give triplet state. Clear? Okay. Now by using some selective methods we are preparing singlets. Two types of singlets are known for molecular oxygen. First singlet, two electrons initially same spin or not? Now two electrons with opposite spin, but the two electrons are present in one pi star antibonding orbital. Now second possibility, same. Two electrons with opposite spin in two pi star antibonding molecular orbital. So like this. Points are remain same, but two electrons in two different molecular orbitals. By applying some energy we can create this. Okay, but normally triplet state is a real state. So normally they will write in quantum chemistry, they will represent like this. See, what is this? See, while I am writing that molecular orbital of oxygen, I retain 2 electrons with same spin. Is it singlet or not? Singlet? No, it is triplet. That's why I written O2 3. Initially triplet. Then 2 types of singlets we can create. What are the 2 possible singlets? These 2. 2 electrons with opposite spin present in same orbital. 2 electrons with opposite spin present in 2 different pi star antibonding orbital. So if they are present in 2 different, they should be represented by summation symbol. Both are gerade orbitals, all are gerade. If 2 electrons present in 1 orbital, that is delta. So this is called triplet, singlet, singlet, delta nothing but only 1 orbital, summation nothing but 2 orbitals. Here plus indicates that opposite spin electron, minus indicates same spin electron. Clear? So now, how many singlets are known? 2 singlets, but real singlet is this one only. Because it is high energy. It is less energy singlet. High energy singlet is not suitable for oxidation. Only less energy singlet is suitable for oxidation. So between these 2, which is a less energy singlet? First one. See, here writing singlet left side, writing singlet right side, both are different. Both are not same. See, if I write left side O3, if I write left side 1, these 2 are same. Suppose if I write 3 right side, then 2, 1. So this is belongs to this one. If you right side these 3 right side, then write 1 if you write, these 2 are same. If you write 3 left side, write down 1 also left side. On that time this singlet right side. So this representation depends on this one. Okay? Suppose if I write a triplet oxygen 3 and I want to write corresponding singlets. If 3 is this, O2 1 means this one. 3 left side, 1 is also left side singlet. If 1 is right side means it is a second singlet. Suppose if I write triplet like this, O2 3, then if I write O2 1, which one among these 2? This one? First one or second one? First one. Clear? So always remember, for oxidation point of view, every time low energy singlet is suitable. Low energy singlet suitable for oxidation. High energy singlet is not suitable for oxidation because not easy to generate. Almost all energy is double to generate that singlet oxygen. It is 94, it is 156 kilocalorie per mole. So means this singlet out of these 2, this is not suitable for doing oxidation. Always not in this concept, any concept. If any molecule gives more than 1 singlet, low energy singlet suitable for oxidation, not for high energy. Clear? Right. Always low energy singlet suitable for oxidation. Always low energy singlet suitable for oxidation. Now go for generations. Preparation of singlet oxygens. How to prepare singlet oxygens? Chemical methods to prepare singlet oxygen. Is a triplet is suitable? No. Normally triplet not suitable for oxygen. So our target is to generate singlet. Singlet means which singlet out of these 2? First one or second one? First one only. Consider this one. If I say singlet oxide, this one only always, not this one. So first one, see, hydrogen peroxide reacts with sodium hypochlorite. Okay, so this is loss of sodium chloride water and molecular oxygen singlet. Sodium hypochlorite. Sodium hypochlorite reacts with hydrogen peroxide, that will give singlet oxygen, O2 1. If I write O2 1 left side, right side, what it may be? See, if I write left side, don't think this one. Sometimes I will write right side also. Even if I write right side, that is this one only. Because it was taken triplet oxygen right side 3. Clear? If I write singlet oxygen any side, this number 1 indicates that this one. Even if I write this one right side, your singlet oxygen is this one, not this one. So that is your first method. Decomposition of endo peroxide. This is second method. Endo peroxide and photolysis will give singlet oxygen. Decomposition of potassium chloride in paracids. Take any paracid, KClO3. KClO3 in paracid generates singlet oxygen. So take any molecular oxygen triplet. It is a direct method. Electric discharge. Electric discharge will give singlet. Then one more, take ozone. Ozone, once if it is exposed to UV visible light, then it will give O2 and nascent oxygen 1. Ozone on exposing UV visible light, you will get singlet oxygen. UV visible light and ozone, that will give singlet. This is normal oxygen. Triplet oxygen can be converted to singlet directly by using electric discharge method. Then this is last method, molecular oxygen on exposing with light in presence of a sensitizer. Okay, so that is responsible to give singlet. Photosensitization is also possible. Singlet can be prepared by using a triplet oxygen. Sensitizer 0, photochemical. Sensitizer will give singlet. Intersystem crossing, sensitizer will give triplet. Triplet sensitizer combined with triplet oxygen. So now this energy transfer from here to here. Then what happens? Sensitizer at 0, molecular oxygen singlet. It is a method to convert. They are called sensitizers. By using a suitable sensitizer, triplet oxygen becomes a singlet oxygen. This sensitizer convert by using this method. Some sensitizers has been given for any molecular oxygen. It can be converted to singlet oxygen. Our target is what? Our target is to prepare singlet. Why you are preparing singlet oxygen? Normally triplet oxygen not suitable for oxidation for organic molecules. That's why I am converting triplet to singlet. So you can use UV light. You can use electric discharge, decomposition methods and direct chemical reaction between peroxide and sodium hypochlorite. use any sensitizer, it can be convert say triplet molecular oxygen to singlet. Now energy transfer from triplet to triplet. So some sensitizers I am giving for generating triplet oxygen to singlet oxygen. This is rose Bengal, Ocene, methylene blue, then aromatic ketones. They are very top for generating triplet oxygen to singlet. Rose Bengal, Ocene, methylene blue, aromatic ketones. These are the top photosensitizers which can convert a triplet oxygen to which one? Singlet. When I use any light, remember, so normally they will use like this. Here a triplet oxygen. Now if I use light in presence of a rose Bengal. Rose Bengal means now here sensitizer for triplet oxygen. So now this is going to be converted to what? This one. Like this they will give. Now these two they will give in RO. On that time it will be generated. This will oxidize on organic molecule. Clear? They will write rose Bengal. So what is rose Bengal? It is a triplet sensitizer. It will generate a singlet oxygen by using a triplet oxygen. Triplet oxygen can be converted to singlet oxygen by using rose Bengal in presence of light. Suppose without using light, by using rose Bengal we can't convert this. Light is mandatory. Structure is not important. This is called rose Bengal. It is a rose Bengal structure, not so much important. You can ignore, you can remember name. Here this is oxygen, iodine tertiary butyl hydroxy, iodine tertiary butyl oxygen, and here anhydrate. So a corresponding cyclic ester should be taken, and here all are chlorines. Benzene with all chlorines. This is Ocene. This is called methylene blue. So structures are not important. They won't ask structures. Directly names they will give. You remember a rough knowledge on structures, but they are not mandatory. Only these names are very, very important. Aromatic ketones means very well known. Benzophenone, acetophenone, like that. Nitrogen with 2 methyls. So that is the methods of generating singlet oxygen by using triplet. And there are some photosensitizers which can generate triplet oxygen to singlet. Later on, singlet oxygen will participate in reactions. Now applications. Only 3 applications are there for oxidation reactions. First one, 2pi cycloaddition, 4pi cycloaddition. Now ene reaction, Photo-ene. It is called Photo-ene reaction. First we will see 2pi cycloaddition with photochemically, supra. See, normally if I take any olefin reacts with here carbon double bond, and here I am writing a oxygen and this. What is this one indicates? Singlet oxygen. So when this singlet oxygen is involved, see, there is a 2pi cycloaddition will takes place here. CH2O like this. This is called dioxetane. That is the answer. When olefins reacts with singlet oxygen, this is prepared by variable methods. Then further this olefin gives dioxetane. This dioxetane is unstable. They will undergo decomposition like this. Finally, you will expect a carbonyl compound. It is almost all equal to ozonolysis reaction. Olefins upon ozonolysis will give carbonyl compound. Same reaction. Right? Suppose if I take a normal double bonded group, then what is your answer? So will you get like this or not? Here oxygen further decompose to give carbonyl compound to equivalence. This will migrate and this will transfer. Dioxetane is intermediate, that will decompose to give carbonyl compound. Like this they will give rose Bengal oxygen. It is a direct giving singlet. It is preparation of a singlet by using triplet. What is this multiplicity? Triplet oxygen under photochemically by using a sensitizer. What you will get? Singlet. Here I given singlet directly, but really they will give like this only. Okay, oxygen photochemical symbol followed by either rose Bengal, ozone or methylene blue or aromatic ketone. If anything is given, it is simple ozonolysis of olefin. So simply break this. Here you will get intermediate like this. Here oxygen, break this bond. Break here and migrate. So here it is aldehyde and here is also aldehyde. That is the answer. You need to know how to write products. See, here this is double bond OET and here also I am writing OET. Molecular oxygen in presence of this is ozone. What is the answer? What is your answer? Can I break this? If I break this, what is your answer? This is double bond hydrogen and this is OET or not? How many equivalents? 2 equivalents. Right? Esther. Break this double bond, put oxygens similar to ozonolysis as it is reaction. Four pi plus 2 pi cycloaddition. 4 pi plus 2 pi cycloaddition possible, but this is not Diels order reaction. Okay, Diels order reaction possible under thermally only. It is not possible under photochemically. It is a photo oxidation of diene. We are not using dinophile. We are using a dinophile in the form of molecular oxygen. See, here I am using diene and here it is a singlet oxygen. Is it diene or not? And what is this? Dinophile. Molecular oxygen is a dinophile. And what is the condition over here? Photochemical or not? Photochemically this I generated. Okay. Now this will combine and this will combine like this. Now you will get a adduct. Like this. Adduct formation takes place. That is the answer. It is a photo Diels order, but it is not excellent reaction. Reaction possible, but thermal photochemical conditions are not preferred for Diels order. It is not real Diels order, because if you take 4 pi partner and 2 pi partner, then what is this? One should be supra, other should be andra. Or else 4 pi antra, 2 pi supra possible. Both supras not possible under photochemical. That's why 4 pi, 2 pi we can write the answer, but this is not an excellent method. Clear? Photo deals order. Photo deals order not exist, not possible. In examination they will give like this. Photo deals order. Photo oxidation, deals order, now it is oxidation. Diene will be get oxidized. So what is your answer? Can I write like this? In interconversion this reaction is important. So this will attack here, this will migrate and this will transfer. And here also remain same. One more, you write down this crown downward direction. Now here you write oxygen here like this. So this will combine and you will get this answer. This is called endo peroxide, this is exo peroxide. Two are possible. Here also endo exo, but phenyl substitutions are changes. Here also two products are possible. Endo is major, exo is minor. Endo epoxide means one oxygen above, other oxygen below. Exo epoxide means two oxygens are one side. Thick line and here also thick line. Here one thick line and one dotted line. That is called endo. So this is stable. Exo is stable. This is stable and endo is found to be unstable. Major populating, unstable population. Endo decomposed to give, starting one question I give in preparation, generations. First one hydrogen peroxide with sodium hypochlorite. Next is decomposition of endo. Endo can break very easily because it is suffering from strain. Large distance is there, below one oxygen, above one oxygen. So this we can write clearly like this. So this you can write like this. Two bonds are above direction. See, this is above and here also it is above. So if two bonds are above, it is found to be stable. This is called exoperoxide. So this molecule we can't write. One is above, other is below. Molecule is suffering from strain. So we can ignore this one. If this is given, it will decompose to give anthracene. It will give this molecule very fastly because it is found to be unstable. Photo-ene reaction. Last reaction for photo-oxidation, photo-ene. See, normally what is ene reaction? Transfer of allyl hydrogen on unsaturated molecule followed by CC bond formation. Okay, this hydrogen migrates from here to here, CC bond formation takes place. This will take this hydrogen, this will take this. So finally I can write like this. This is called ene reaction normally. Photo-ene reaction nothing but same. Transfer of allyl hydrogen on singlet oxygen. Now this bond migrate here, it will attach on this and this will take this oxygen. Now this reaction is possible under photochemically. So put double bond here. Now this carbon attaches to oxygen, next here hydrogen over here. That is the answer. So this is called allyl hydrogen peroxide. Up to here it is allyl, here hydrogen, here peroxide. This is called Photo-ene reaction. Transfer of allyl hydrogen on singlet oxygen followed by CO bond formation. CO bond formation, that is called Photo-ene. What is normal ene reaction? Transfer of hydrogen followed by CC bond formation. This is thermally possible, but what about here? Photochemical. I am not writing photochemical symbol. Why? This singlet oxygen generated by triplet oxygen, that is a photochemical reaction. Remember, suppose if I write a normal oxygen, then here should I write photochemical symbol or no? Yes. Then should I write rose bengal? Rose bengal. If I write photochemical rose bengal and this oxygen becomes a triplet to singlet, then that singlet will participate in reaction. That's why I am not writing this all. Simply I am writing this symbol as 1. If they given 1, they won't mention photochemical symbol, they won't mention photosensitizer. Suppose if they not mention 1, means it is a triplet oxygen. On that time they will mention photochemical symbol with a photosensitizer. Okay? So that is Photo-ene reaction. Here you write transfer of allyl hydrogen on molecular singlet oxygen followed by CO bond formation. CO bond formation to give allyl hydrogen peroxide. Is Photo-ene reaction. Normal in reaction thermally preferred, this is photochemically preferred, but photochemically it is not excellent reaction. If they given photochemical, first to convert triplet to singlet, then singlet will participate. Transfer of allyl hydrogen to molecular oxygen, then that to molecular singlet or triplet? Singlet oxygen. Then followed by CO bond formation. Transfer of this hydrogen followed by CO bond formation to give allyl hydrogen peroxide. So this is further on treatment with Na2SO3, sodium sulfate or sodium borohydrate, NaBH4. So this bond is going to be cleaved here, then there is a formation of allyl alcohol. So this interconversion is important one. Sodium sulfite, Na2SO3 or sodium borohydrate. So this peroxy bond cleavage takes place and forms allyl alcohol. Okay, add one hydrogen here, this becomes loss of water. Loss of water takes place followed by allyl alcohol. Up to here it is ene reaction, Photo-ene. From there onwards reduction reaction. Reduction of hydrogen peroxide, alkyl hydrogen peroxide to give corresponding allyl alcohol. So from year to year, questions are coming. So transfer of allyl hydrogen on molecular singlet oxygen followed by CO bond formation to give allyl hydrogen peroxide is Photo-ene reaction. In Photo-ene reaction, what is the answer? Photo-ene reaction, answer is allyl hydrogen peroxide. See, it is concerted reaction. It is concerted reaction. It is a regio and stereo specific reaction. Alkyl hydrogen peroxide on reduction produce allyl alcohol. It is very important one. Remember, this point I am writing separately because it is asking in exam. This step they are asking. It is a concerted reaction, regio and stereo specific reaction. Okay, so if it is a regio stereo specific reaction, see, if any molecule having more than one double bond, highly substituted double bond is highly substituted double bond involved in reaction. If only one double bond is a no problem. If molecule having more than one double bond, which double bond is participate? Less substituted or more substituted? More substituted. Because it is a nucleophile, it is an electrophile. If it is a more substituted, more nucleophilic, then it can act with a electrophile. So always allyl partner is a nucleophile, it is a electrophile. Molecular oxygen is a electrophile, allyl should be acts as a nucleophile. So more nucleophile means more double bond. Right or not? So indirectly I am saying that allyl skeleton is a which one? Nucleophile or electrophile? Nucleophile. And singlet oxygen is a electrophile. These points are very important. In your examination, these points they will ask. Regio stereo specific. Answer is alkyl hydrogen peroxide. Alkyl hydrogen peroxide can be converted to allyl alcohols by using some selective reducing agents. This point is important. Then when any molecule, see here I given only one double bond. Suppose if any molecule having more than one double bond, whichever double bond having more donors, more alkyl groups, or double bond having more substitutions, only donor, only that double bond involved in reaction. And very important thing is, if it is taken with a more substituted double bond is major, in that one always double bond formation takes place at terminal. See, here already one double bond is there or not? Here one double bond is there or not? Is this double bond is disappearing here? Double bond is disappearing and we are getting new double bond or not? This new double bond always want to settle down at terminal. They don't try to create double bond at internal. If any competition comes between terminal and internal, try to create that newly formed double bond at terminal. If more than one double bond is there, which double bond is selective? More substituted. And if you create double bond at internal and terminal, which is preferred? Terminal. If you know these 2 points, you can attempt one question on Photo-ene. Clear? So what is the meaning of concentrate? Single step reaction. Okay? 2 pi, 2 pi, 4 pi, 2 pi, Photo-ene, all are single step reactions only. So they will give like this: molecular oxygen photochemical, rose Bengal. So if you know that points clearly, you can pick the answer. How many double bonds are present? 2. Suppose if molecule having more than one double bond, which is selective? More substituted double bond. Is it more substituted? How many substituents are present here? Here how many substituents are present? 3. And what about here? Only 1. So which is preferred? Below or above? Below. Now suppose see below is preferred, in that it is also allyl, it is also allyl. Right? Now this is saying that select this double bond. And what about this point? Allyl skeleton is a nucleophile. See this. If molecule having more than one double bond, highly substituted double bond is involved in reaction. Okay? So next point. Always try to select a double bond such a way that it will give terminal double bond. Suppose is it allyl? Is it allyl or not? I am selecting this double bond, it is allyl. Is it allyl? Yes, it is also allyl. Now suppose if I select this one, here double bond, then what is your answer? Can I write oxygen, hydrogen or not? Right? So remove this bond, this will attack on molecular oxygen, and that O minus will take proton from this hydrogen. Suppose if I take this one, if I take below, can I put double bond here? If I take this hydrogen, then this will attack on this one. So which is major? Second one or first one? Second one. This is major, it is found to be minor. More substitute double bond and try to create double bond at terminal, because it can easily take hydrogen. It can easily even lose hydrogen from allyl carbon. So here what do you expect? What is A? Here this is double bond and it becomes OOH and break this. Here two hydrogens are there, migrate here and attach to molecular oxygen. Over. So that is about photo-oxidation. Only three famous reactions are there, 2pi 2pi, 4pi 2pi, one more is photo-ene reaction. Photo-ene reaction will give allyl hydrogen peroxide, that is on reduction will give allyl alcohol. Okay, so that is end of photo-oxidation and that is end of photochemistry. So complete photochemistry is over. We discuss complete pericycle as well as photochemistry. So some questions which I given in your WhatsApp group. Pericyclic reactions photochemistry questions are given. So your first task is you need to prepare total pericyclic chapter as well as photochemistry chapter, and that questions we will do directly in your class by opening that folder. Okay, that each and every question solution I will explain in your regular class only. But before starting off that questions, everyone try to prepare total concepts of pericycle and photochemistry. You try to prepare at a time. Okay, total electrocycle, cycloaddition, sigmatropic,